Chalo, what I'll do is I'll just do a review so people who come late just miss out on the review. Okay, so I'll start from this. We had done Jensen's inequality. Um, well, we had defined the integral. Let's see. Just give me 1 second. Huh? Yeah, this was the big integral. Then we extended the integral some properties. Let me just do this example one more time. It's just an example that you should keep in mind, right? This is, when does xn converge to x almost surely, but the expected value of xn does not converge to e of x, right? We did this last time. And the idea was to look at a random variable, xn omega, which is n between 0 and 1 by n. So it's kind of, its value is going to infinity uh, with a mass which is going to 0. Together they have e of xn equal to 1. So these are kind of situations you have to worry about, where random variables may be becoming large, but with small probability. Then you have to worry about whether you can interchange the expectation and the limits. So in this case, as we discussed, for every omega you can think of, omega is in this space. This is 0.0, this is 0.1. Every point here is a outcome of your experiment. On every point here, you defined a random variable, x and omega. It's 0 everywhere except between 0 and 1 by n. So for n large enough, for every omega which is positive, xn omega is going to become 0. So in particular, xn will converge to 0 almost surely, right? Except at one point. Uh, and e of x is equal to 0, as we argued last time. But e of xn is always equal to 1. So in the limit also, it's equal to 1. It's not equal to e of x, which is 0. Any questions on this? Is it kind of clear? So this example is clear to everybody, right? Okay. So the bigger question was, when we have xn converging to x, when do we have expected value of xn converging to expected value of x? In particular, this is the limit of expected value of xn, right? When is this going to be equal to? This guy is x. So when will that be equal to expected value of x? So when can we interchange the limit and the integral operation? Right? And one sufficient condition is monotone convergence theorem, where basically all your xn's are non-negative and they're non-decreasing. In that case, xn is increasing to some x. X could be infinity at some omegas. And this will imply that e of xn is going to converge to e of x. Yeah, it's weaker, right? You could have functions which are increasing and converging to some other function, but not uniformly. But even then, this limit and exchange holds. And dominated convergence theorem. So if there's a random variable y which dominates each and every xn in absolute value, expected value of y itself is finite. So it's not letting mass escape away of any of these xn's. Then xn going to x implies e of xn converges to e of x. All right, Jensen's inequality we did last time. So I'll just quickly state it, that if phi is a convex function, then expected value of phi of x is greater than or equal to phi of expected value of x. Right, so let's carry on from this. And then we did a example of non-measurable set. Everybody was comfortable with that example? Paran, this is okay?
Do it once more.
You can do it once more. It's good to kind of just, bring it home to yourself. It's very simple. Your space is all the points on 0 to 1. We just make it circular. Okay, that makes life easier. It's convenient. Now you take any arbitrary point x here and collect its rational neighbors, right? All the points which differ from it by a rational number, that becomes one set. Take them out. Take another point, collect all its rational friends, take that out. So you get uncountably many sets like this. Each set is of countable length. So if you had countably many sets, that would have been total countable number of points. That, of course, is not your space 0 to 1. 0 to 1 is uncountable space. So each set will have to be uncountable, right? And what we'll do is we'll use the axiom of choice to collect 1 point from each of these sets, right? Each set again has countably many elements. There are uncountably many sets. We take 1 point from each of them. We get a set with uncountable number of members. Axiom of choice allows us this, right? So that's going to be a set B0. Mm-hmm. What's that?
Uncountable amount of sets. But just out of curiosity, for every rational we pick, the set looks the same. So it's the same set. Because it's differing, it has the difference of all other rationals.
Yeah.
So that set is the same regardless of what rational.
True. So it's true that if I start with a rational number, I'll collect all the rational numbers.
And so that set just remains. But
That's
I
it.
get that.
Yeah, yeah. Right. Okay, so now we constructed the set B0, where we took one element from each of these sets. So once we got B0, we can also collect elements in each and every set which differ from B0, element in B0 by number R, any rational number R. So we can construct BR. BR has exactly the same number of points as B0, right? For every R. So B0 we got because we looked at each and every one of those sets. We took just 1 point from there. Now go back to those sets. Any one of those sets, if it has X, it also has X plus R. For any R between 0 and 1 rational. So let's now construct a new set where we take X plus R from every set. And that's your BR. So I have B0, BR, and BR for every rational R. So I have countably many sets now. BR, basically, countably many sets. These are non-measurable sets.
We're taking any R.
Any R between 0 and 1. I'll go through the whole circle that way. I'm interpreting 0, 1, I can go around the circle to find that B plus X plus R element. Okay, so you've got another set BR which has same number of points as B0, and you've got this for every rational point R, and these are disjoint sets. They won't have anything in common, right? So these are non-measurable sets now. Because I have countably many sets, I don't know what measure to assign to them. You say positive measure, then the total measure becomes infinite. Total measure should be 1. If you assign 0 measure, total measure becomes 0. So, I can't assign measure to these sets. All this methodology that I have where I said assign.
Because uncountable, that's why it's. Yeah.
I can give you uncountable sets where I can assign measure. All the points between 0 and half. That's an uncountable set, measure is half. This is a very special set that I've constructed. Where my
What's going wrong? I'm not understanding.
Why can we not assign measure to it? Well, you have to kind of go back to how did we assign measure. First of all, it's just clear that we constructed this set, and if we assign measure to it, we run into a problem. Because if we assign positive measure, then we have a problem if we assign 0. Yeah. Then your point was, why could we not assign measure to it using our methodology? Because what was our methodology? Our methodology was, let's assign measure to intervals, let's assign measure to union of intervals, and Cartier-Dori theorem tells us that it extends to sigma algebra containing those intervals. So that sigma algebra does not contain these sets. So we've not been able to assign measure to these sets. If it was in that sigma algebra, then we'd have no problems. Right? And there's a vast theory of these kinds of sets. But we won't talk about that right now. Okay. Should I also go through this we showed last time? We're just doing a review right now. we showed that, this daunting looking thing, when does it look like this familiar, friendly thing? Hx is, for example, x squared. When are the two the same, right? And the one thing always is that, I say this to you because I know I was always daunted by this. So, that's why it's good to say that's just a friend. Hx, think of it as taking a limit of finitely many values. It takes finitely many values and probability assigned to the set where it takes those finitely many values. You sum that up, that's what this is. Just you have to take a limiting operation. Hx lies in subset and then. Yeah. So it should not be daunting to begin with. Integral should never be daunting. It should just be summation, basically. Finite sum is a good way to think about it, but it's actually a limit of it. Right? Now, in this case, why do these turn out to be equal? Well, the thing was, how did we define the density function? For a random variable, we define the density function as follows. That's how we start. We say x has a density function, small f, for giving probabilities to it. If x lying in any interval b, more generally Borel set b, is given by integral of fx dx. That's how we start. This is not something that you derive. That's what you assume. This is how probabilities are assigned, right? So that immediately tells you that if my h of x was just an indicator function of x omega lying in a set B, right? Then by definition, this is true. This property is true. For h of x being an indicator function, by definition, it's true, right? Any confusion on this so far? Lots of notation floating around. Now you've got it for indicator functions, then it's also true for simple functions. And simple functions are not that simple, right? They approximate complicated functions really well. So that's what we did. We said, okay, let h of x with this simple function, then hx dp is just integral of this simple function with respect to dp. Since it's taking finitely many values, it's just summation alpha k, probability of b of k, the set where it takes value alpha k. And then p of b of k is just this integral. And now you can go back, so you have hx dp is, because now I'm looking at x lying in bk now, right? This alpha k into indicator of x lying in bk, that's this function right here, with respect to fx dx. And that's exactly hx fx dx. So basically all I've done is I've just taken this summation inside here. Finite summation, I can always do this. Property of linearity of integration. And that gives me this quantity right here, and that's exactly this quantity right here. So everything is working out nicely for simple functions. For more general functions, you approximate them below. For non-negative functions, you approximate them from below by simple functions. Then you get this relationship to be true for simple functions. Take monotone convergence theorem, take limits on both sides, and you get it true for non-negative functions. And then if you have a general function, you break it up as a difference of two non-negative functions. Show that this is true for non-negative functions separately, and just take the difference. So it goes right through. So this is the methodology. There's no way around it. It's called standard technique. So many complicated results are shown simply this way. Not all, by the way. You don't have to see any problem and just start applying this. You have to think about the problem. All right, so I won't go through this slide. And then we did notions of convergence last time, right? We discussed all of them. Any questions on this slide? So we know what convergence probability means, right? So this xn converges to xn probability. If this quantity right here, for any epsilon, you give me an epsilon, fix it, this probability should go to 0 as n goes to infinity. This is more complicated. This is saying, let's go to each and every omega and see whether we see convergence or not. We get a sequence x1 omega, x2 omega. If we get convergence, it belongs to our set, otherwise it doesn't. Collect all the omegas where this happens. That set should have measure 1. Then we say almost full convergence. And then we just differentiate it with pointwise convergence here and uniform convergence here. Okay. Okay, so let's now move on to our next set of slides. This is still review. So we first said, let's come up with an example where we have convergence in probability, but not almost sure convergence, right? So just get familiar with all the ideas. In this case, this is our sample space omega. All these points, that's your omega, right? We are going to define a probability measure, which is again a big measure. So probability assigned to an interval is length of the interval. And we'll define now sequence of, I guess, random variables. So C0 is 0, right? Actually, just numbers, not even random number, this is number. C1 is C0 plus 1 mod 1. So C1 is also 0. C2 is 1 plus 0 plus 1 by 2. So C2 is 1 by 2. C3 is 1 by 2 plus 1 by 3. C4 is 1 by 2 plus 1 by 3 plus 1 by 4 mod 1, so on and so forth. But pictorially, what we are saying is that C2 is, well, C2 is just this line right here. This is C2, this is C1, and random variable x1 is going to take value 1 on this interval and 0 everywhere. Basically, now we're defining random variable x1 on each and every point, right? Random variable is a function on every omega. We assign a number. This is a nice function. It just takes two values. So showing that it's measurable is not a problem, right? Inverse image of any Borel set is going to be in this underlying Lebesgue measure that you have. Okay, so measurability, all those issues, it's good to kind of tie them up, but in our kind of world, these are usually going to be true, but you should tie them up at this stage. So this is your random variable x1, your random variable x2 is going to be random variable which takes value on these 1 on these points and 0 elsewhere. Then x3 is going to be, I'll just go, this was 1 by 3, so maybe I'll go 1 by 4 here. Okay, it doesn't look right, but you get the idea. Let me make it look slightly better. So it's x3 is, right? x3 is 1 here and 0 elsewhere. Similarly, you can define x4. Basically, I'll just take this piece of pi and keep on moving it around. Pi defines the region where your x corresponding xn is 1, it's 0 elsewhere, right? So everybody's with me on this, right? What the underlying probability space is, underlying sigma algebra, random variable, induced measure, all those things you can figure out. Okay. So now probability that xn is 1 by n for all n. So you can see that probably that absolute value of xn is greater than epsilon for any epsilon less than 1 and positive is going to be 1 by n. And that's going to go to 0 as n goes to infinity. So xn is converging to 0 in probability, right? If you look at this picture for a very large n equal to 200,000, very small region where the random variable is taking value 1, otherwise it's taking value 0. So as n increasing, the random variable is increasingly taking value 0 at most points, right? So that picture is clear? Okay. But on the other hand, as we know from this picture, our pi's are going round and round on this circle again and again. So any point I take here, it will be covered by some pi infinitely often. So random variable xn will be equal to 1 at this omega infinitely often, right? Infinitely many times. So on this omega, if I see the sequence x1 omega, x2 omega, x3 omega all the way, I will not see convergence to 0. Because no matter how far I go, I still have a random variable which becomes 1. It's not going to be 0. Is this kind of clear to everybody? And that's true for every point here. So this is very nice. Otherwise, one gets so confused by these ideas, almost sure convergence, convergence probability. But this really makes it very, very clear. Okay. So that means that probably omega such that x and omega is equal to 1 infinitely often. That is there a question in the chat? Oh, no question. All right. So that tells me that the probability of seeing convergence is actually 0. So xn does not converge to 0 almost surely. Okay.
So we can see something stronger than xn doesn't auto surely converge. We can say that at every point xn doesn't converge.
That's right. Yeah. That's why it does not converge almost surely, meaning the set weight does not converges. Yeah.
But that at every point that doesn't converge, that's why P omega is the measure of that entire set is 1. But if you reach omega doesn't.
No, he says rather than saying almost surely, you can say everywhere. Yeah. Okay. So now let's go in the other direction. Let's show that convergence. Yeah.
But is there any such
Just repeat your way. Somehow I don't pick up your frequencies very well. Huh.
Yeah, basically, the convergence
Mhm.
is about the measure of the set in terms of mean.
Mhm. I see. I mean, as such, of course, the statement itself is clear, right? The set where xn and x differ by more than epsilon, that's a tiny set for n large enough. That part is clear, right? But the set where you have convergence could keep changing. That's the interesting part in probability. Now, what you can say, however, and that's a good homework exercise, Anirban's listening, hopefully Anirban's listening, that even if you don't have convergence, if you don't have almost sure convergence, there's a subsequence where you have almost sure convergence. So convergence in probability implies that there's a subsequence where you do have almost sure convergence. So that gives you more intuition as to what you can say.
Probability implies there's a subsequence, so it's almost all.
Where you do have almost sure convergence, yeah. Huh?
You need some more bits.
No. As long as you have convergence probability, you have convergence almost surely along a subsequence. No. You already have convergence probability. So you have a lot already, yeah.
I guess.
Right? So yeah, think about how to solve this. Anirban is on the homework, right? Yeah. So now we are all set. All right, so now let's go in the other direction. Continuity of probability measure. So we'll need this idea to show, it's a generic idea, of course, but it's a good segue towards this. We also want to show that convergence almost surely implies convergence in probability. We've not shown that yet. It seems to be true, but you have to kind of show it. So we'll use this idea of continuity of probability measures. This is a generic property.
Because you're saying it's the limit converges for
Hmm.
all omega, where this
That's
measure of
right.
this omega is 1.
That's right, yeah.
And then that just immediately tells you.
But you have not immediately. You still have to show that this implies that the definition of convergence probability that we've come up with.
You just want to somehow take within sight the that.
Yeah, that's it. So we'll just spell that out. It's good to spell these things out because it's easy to make mistakes. So let's see. So first we'll have this idea of, we have this idea of points, sequences increasing to another limit, right? So let's extend that idea to sets. It's a very natural thing. If I give you a sequence of sets which are non-decreasing, they're only getting more and more points, then what does the limit mean? Right? A1 is less than or equal to A2.
A1 is, what does less mean?
Contains less point. You contain in.
Less than, cardinality is less or it's contained in?
What you said earlier, contain in. So A1 is smaller than A2 if A1 is a subset of A2. A2 is smaller than A3 if A2 is a subset of A3, so on.
So then, why does union matter? N will contain all previous things anyway. So why do you take union?
No, but you want to have a union which contains all the AN.
Yeah, but
no AN will.
already contains the previous guy.
A 10,000 contains previous, but it doesn't contain A 100,000. A 100,000, 800,000 contains previous, it doesn't contain what happens later. So you need an idea of something which contains all of these sets. It's a very natural notion.
I don't get why not AN where N goes to infinity. Like, why do we need the union?
That's my point. So A1 is a subset of A2 is a subset of A3, that you agree, right?
That's how we would define small.
That's how I'm giving you a sequence of sets so that they're increasing sequence of sets. They're becoming bigger and bigger. Now, my point is all of them are, it makes sense to think of union of all these sets. Now, your point is why look at the union as it is A 100,000 contains all the sets up to A 100,000. But A 100,000 does not contain A 101,000.
Then you look at it and
Then you look at 101,000, but that doesn't contain 102,000. So you see it's unsatisfactory, right? So it makes sense to have a notion of union of all these sets. It's good to kind of have this discussion.
So, I mean, just to be clear, here, there's also something that A1 is contained and A2 is contained.
That's right,
That
that's
is
right,
it.
that's right, yeah. Yeah, so this is what I mean by this picture, by this notation. AN is increasing to A means that AN is contained in AN plus 1 for every N.
Oh,
Right.
okay.
So you will be on this, right? Huh. So now that we've got this idea of sets which are becoming bigger and bigger, we can define this very nice idea of limit of these sets. You know? So limit of AN, so this is a new idea, and that's defined as this union of all the AN from N equal to 1 to limit is called the union. That's the definition. And this limit is defined only when the sequence of sets is monotone, in this case increasing. We'll just quickly see. I mean, it's very natural how we'll do this when it's decreasing, right? How will we do this when it's decreasing? Intersection. Yeah, B1 is bigger than B2 is bigger than B3. All of these contain the intersection.
That is eventually converted.
Should it? Let's say B1 is equal to B2 is equal to B3. Yeah, yeah. I mean, one can do all kinds of things, right? I can always take sets 0 minus 1 by n, 1 plus 1 by n. Now let's shrink it. It converges to 0, 1, not to 0, not to empty set. All right. So the point is when we do this, then P of AN is also a non-decreasing sequence of numbers. So it's a very natural question to ask that is it converging to P of the limit, right? Is it always converging to P of the limit? Huh?
But haven't you written that it will?
Yeah, that's right. Let's just pretend the suspense. Okay. Yeah, these notes should be written that maybe next time. Now that I have a LaTeX version with me. All right. So the point is, it's not obvious that this is true. It needs to be shown. And why it's true is embedded in the property of countable additivity that we use to define probability measure. Because probability measure was countably additive, this property followed. It would not have been true if I didn't have that property. If I had finite additivity, this would not be true. We'll show this in a moment, huh? Yeah, in this case, it's AN has to be a non-decreasing sequence of sets. Well, so that's, I mean, the point is this, AN is increasing, that part is clear. And then I'm just saying this set is well defined. It's just collect all the elements which belong to some AN. So it's a well-defined set. And now I'm saying AN is converging to this guy. So there's no other notion of A needed. Right?
this is how we're defining the limit.
That's right. That's how we're defining the limit. Yeah. Okay. And now the question is it true that P of A of n is converging to P of this limit? That's the question we're answering. Turns out to be true, but it needs to be shown. And you could have Bn, which is a decreasing sequence. And then you can, limit of Bn then becomes the intersection of all these sets. And then the question is probability of Bn decreasing to probability of the intersection? Can you see that the first one implies the second one? Is that part clear? So this implies this, right? We just take the complement basically. Yeah.
The reason it implies this is because my measure is finite. If I didn't have a finite measure.
It's all probability. Yeah.
Right. If I don't have unknown,
then of course, yeah, then you have to assume, make some more assumptions.
with finite measure that zero, like
I mean, if my underlying measure mu for B1 was infinity and mu because B2 was infinity, then you have to be more careful. Yeah. Spoken like a guy who's already done measure theory. All right. So how do we prove this? Let's just look at the proof. So you define Cn to be An minus 1. Whatever is new that An is bringing to the table, that's your Cn. Now you could say that, okay, I could have looked at, if A1, A2, A3 was not a non-decreasing set, even then I can define An to be, Cn to be the set which is whatever is new. So then I'll have to account for the other sets as well. But right now I don't have to worry about them. Okay, so Cn is defined as follows. So what's nice about Cn now, the Cn sets? They're disjoint now, right? Is this clear? They're all bringing in points which are not there. And union of ai equal to 1 to n is just an, but that's also your union of ci, I from 1 to n.
Yeah.
But the thing is, now I can use countable additivity, right? So probability of this union is just summation of these probabilities, which exactly is this quantity right here, which is exactly this quantity right here. So nothing much being said here. An is exactly this set. So far so good. But we want to talk about, sorry. We want to talk about limit of these numbers, right? And we can talk about limit of these numbers. That's how it works out, right? So probability of this countable union of CIs, because they're disjoint, by countable additivity property, that's this infinite summation. They are disjoint sets. So we have this already. And this is limit n, limit of these finite sums. So this is exactly limit of P of A of n. So P of A of n is converging to this limit, which is exactly equal to P of probability of the union of the AI, right? Because union of CI is same as union of AI. Every point here is there, every point there is here.
how could we just say that this sum limit is conversion? Okay.
How do we say that?
That's just because CIs are disjoint, and then we could just use the idea, like definition of probability to see.
I mean, yeah, this is how this, maybe we assume that the probability measure satisfies this property.
So all we did was took this increasing sequence, made disjoint, said, okay, probability tells us limit exists, take it back.
That's right, yeah. So that's why it was already there in the countable additivity, yeah. So this exactly means that this is this quantity, right?
Wait,
That's a definition of this quantity here.
I still don't understand how can we surely say that the limit exists?
Well, that's what I'm saying, that when I defined probability measure and I said that this is true, what I'm really saying is that this quantity here is equal to this quantity. Because this summation is nothing but the limit.
Oh, yes.
What is this summation? This summation is actually this limit here.
Yes.
So I'm giving you that this limit exists. It's given to you, yeah. All right. Sorry. Okay. So Dhruman, can we move on? You told me last time I was moving too fast on slides. Okay.
I want them to read.
So have you read? All right. Yes. Chalo, theek hai, yeah. But just slow me down if you think that things are moving fast. Okay, now we come back to the problem at hand. And as as Rushil had kind of guessed, it should be easy to show this. Xn going to X almost surely implies Xn going to X in probability. Should be easy to show this. But what does Xn going to X almost surely mean? Do you agree it means that this set has probability 1? We discussed this, right? Or was this still a homework problem? No, I mean, should I still give this to you as a homework problem, or actually let's Anirban, let's have this also as a homework problem. This is in, yeah, we can have it in this context, or actually in this context is fine. I mean, essentially, you have to ask yourself, what does it mean for the limit to exist, right? For every omega, a sequence has a limit. If I give you any epsilon, that means for every epsilon, that means for every 1 by m, there exists n large enough. So there exists comes in the union, some n, and thereafter you're within epsilon. X and omega minus x is within epsilon. So now you can argue if omega is here, it must belong to this collection here, and vice versa.
So the only reason to bring in these union and intersection unions is because we're dealing with probability. But other than that, the argument isn't tough. Right? It's just because notation becomes.
We want to show that this set is measurable.
So now you have to that because you're worrying about P, you brought in
That's
the
right.
intersection.
Yes, yes.
But the idea isn't.
No, but it's a big point that, Cartier-Diori's theorem has already told us what the probability of this set is. That's an important idea, yeah. We define it for simple sets like this.
Oh, and then you extended it to your sigma algebra. So
Yeah. So, these sets we could assign probability to, and then, so we could presumably through these sets we can assign to an algebra, and then it extends to sigma algebra, and this whole set belongs to my sigma algebra, and hence this set belongs to my sigma algebra. So it's a well-defined set. So there are a lot of other things one could talk about when you do a proper course in measure theory. You'll talk about sequence of random variables, lim sup of random variables, lim inf of random variables. You'll have to do that in your analysis course. All right, so now we agree that we have that this set has probability 1 for every m. So then do you agree that this is equal to 1 for every m? It's a bigger set, right?
Yeah.
If the smaller set has probability 1, then the bigger set has probability 1 for every m. Everybody with me on this? But then, well, let's go a little bit slower. Do you agree that then I can put epsilon here? For every epsilon, so it's true? Why is that the case? What's the proof? Yeah, since it's true for if you give me an epsilon, I can always select a 1 by m which is smaller than that epsilon. For that, this is 1. So with epsilon, I get a bigger set.
you want one man to be greater than epsilon.
No, less than epsilon. So for that, I have this set is already 1. With epsilon, I have a bigger set, must be 1 there also. Right? Okay. And now I've just taken the complement. Right? So if this is 1, then this must be 0. Right? That's exactly the negation of this. All right. Okay. So far, so good. Ruman, can I move on?
Yeah.
Okay.
Prof, can you tell like give me the intuition again of what the unions and
Yeah.
you told us earlier, but
This one here. Yeah, no, I mean, it's just kind of, you'll have to do this as a homework problem, but the idea is what is the definition of a limit? For every epsilon, which corresponds to every m here. Because for every epsilon, I can find 1 by m, which is slightly bigger, slightly lower. So for every m, there is some n. So I belong to some n. I belong to this union, basically. So that thereafter, for all small and bigger than that n, this property is true. Right?
for all the
What's that? I mean, the limit definition is eventually you're arbitrarily close. So it's for all n. For all should be intersection, right? For this and this and this and that, yeah. Yeah.
And then we say in the end that for all n,
Hmm.
there exists some n equals to n, where the probability of this thing is 0.
I mean, I would just let you think about this, but when we define a limit, we say for all m, meaning for all epsilon, there exists some n, some big N. So that for all small and bigger than that big N, these guys are not 0, but they are very close to each other. They are within epsilon, within 1 by m of each other. Right. So let's collect all omegas which have this property. So you'll tell me that if I've taken omega from here, so it already has this property, then you'll argue that that omega must belong to this set, this whole complete set. And if I give you an omega which belongs to this complete set, you'll have to argue that that omega also belongs to this set right here.
So while the force union will be selecting all these n to infinity, capital N to infinity, such that our condition. Then because we're saying it's true for all n greater than this, we're doing the union. And then we're just saying that because we have the argument there exists an epsilon, for all epsilon, sorry, this is true, we'll take the intersection n.
Yeah.
That's all.
Yeah.
So,
I mean, you'll take omega from here, which we are given that for all epsilon you have nice properties. So hence you'll argue that on that omega, for all 1 by m also you have nice properties. Okay? But write it down cleanly, huh? This thing should, there's no hand waving here.
so we say that for omega x and omega conventions,
Yeah.
we are allowing the convergence to be
In this case, I'm just kind of assuming it's
no
real valued. I could allow it, yeah. But no, in this case, your point is valid. I'm not allowing it to be infinity. Because if you're converging to infinity, then they not be within epsilon of each other. Yeah. So mostly when we talk about convergence, it's about real valued random variables. Convergence to a real valued random variable.
Yes, the reason I asked this was you gave us a problem that the convergence property implies that subsequence converges to almost surely, right?
That's right.
Yeah, so this sounds suspiciously similar to Bolzano-Weierstrass. That requires a completeness condition of the sequence.
No, so it's not that suspiciously similar to. That's only suspicion. But the easier way to show this that. I mean, I can tell you, but you'll chat GPT, you'll get the complete answer. So I'll just let you do that. Right. No, but his point here is very valid that, all of this makes sense because x omega is real value. If it's infinity, then, we need not, because we have sequences which are increasing, but they're not epsilon close to infinity. What does it mean for something to be epsilon close to infinity? Should be sufficient. No. I mean, it's a different issue altogether. Just because the measure is finite, I can still have x omega equal to plus infinity, and x and omega is rising up to plus infinity. And this argument will not fit in there. Yeah. All right, so we are at this point so far. So let's just take stock of where we are. We know that almost sure convergence implies this. We want to argue that it applies convergence probability. Okay? So you can't quite see it here, right? Because what is convergence probability? Convergence probability is just for any given small n, this set for fixed epsilon. Now I fixed epsilon, so that's a good thing. But I want to say that for any fixed n, this probability of this event should go to 0. So that's not immediately obvious from here. It's almost. But it's good to see this very cleanly, unless, it's also fun to do it on your own, but yeah, because then you really understand things. Okay, now we'll use the idea of continuity of probability measures. So let's define Bn to be this set union from big N to infinity of this event. So do you agree that what I have is here is that limit as n goes to infinity, probability of Bn is going to 0. Because this is my Bn set and this is a countable intersection of it. Okay? And probability of the intersection is 0. So that means the limit of probability of B of n is also going to 0. Right? What I'm saying here is probability of intersection of Bn n equal to 1 to infinity. Or actually, let me just use that notation. Bn n equal to 1 to infinity is equal to 0. And Bn is a decreasing sequence of sets. Right? This Bn, the way I've defined it, it's always decreasing.
Yeah.
So then from what we discussed from the limit continuity of probability measures, in the limit P of B of n is equal to 0. Right? Because it's equal to this probability, right?
And that's always.
I get it. I think Bain is union though.
No, but now once that we've defined it, now we know that this Bn, the way we defined, is actually a decreasing sequence of sets.
Intersection of
Because I'm taking union over smaller and smaller number of sets. So Bn is decreasing. Okay. And this guy here is intersection over all these Bn's. Right? The inside part is Bn. So we know that P of the intersection is equal to 0. That means limit of P of B of n is equal to 0. That's what we just did. Right? So now we know that Xn converges to Xn probability if this is true for any epsilon, right? But so how do we complete the proof now? We know that P of Bn, the limit of that is 0.
Yeah.
Now we just have to show that the Bn is actually bigger than this quantity.
Bn is bigger than that.
It's, yeah. It's a union of all the sets, right?
Yeah.
This is, yeah, this is B small n here.
I mean, that is true to the left, the other already in the right. Yeah.
Yeah.
Oh, okay, that's it. And
I think then you just do it for all n.
Yeah, this is true for all n. So let's call this guy an. Then P of an is less than or equal to P of bn. No, no, I don't know what you're saying. All right. This guy in the limit, it exists and is 0. So this guy should also have the same limit and 0. Right? Just go back to definition of limit. This guy is going to be less than epsilon for all n large enough. This guy will also be less than epsilon for all n large enough. So it also has a limit 0. Right?
I think that what is the definition of measure doesn't require monotonicity. So if A is contained, P is not necessarily that lambda of A will be less than equal to lambda. Count the relativity and the fact that it takes 0 outside to 0.
So what's your point? I mean, if
My question is,
no, in the sense that countable additivity is part of the definition of measure.
right.
So you get that P mu of A is less than mu of B if A is subset of B. It's already there, right?
Okay, yeah.
Yeah, that's all.
Like, and order transfer, if you scroll up to the previous page, respective.
Mhm.
Yeah, so can you explain, maybe I'm missing something here. We've said that these two sets are equal. The measure of that set is 1. So I'm not saying how you can compute that the measure of this set is 1. I mean, where did the intersection, the first intersection?
Well, this is bigger than that set, right?
Okay.
If set probability of A is 1 and probability and B is bigger than A, then probability of B is also 1.
And my measure is the probability.
Right? Okay. Okay, so now we have our result. So I mean, it looks like there should be easier ways of saying these things. But nonetheless, it's, once you understand the basics, it's not so hard. This is, yeah. I mean, I guess the point in some sense is, would you have come up with this argument? But it looks like you should be able to come up with an argument like to show that almost sure convergence applies convergence probability.
So the big picture is you've shown that probabilistic convergence doesn't necessarily implies almost sure convergence.
Yeah.
And almost sure convergence
Implies. That's right. That's right. Yeah. Right. So let's also do Borel-Cantelli lemma. This we'll use at some point later, but it's a very powerful tool to show almost sure convergence. The point is that this is a 20th century notion, almost sure convergence. Convergence probability was an older notion. So it's a new notion, it's a very strong notion. You need tools to prove almost sure convergence. So this was a very powerful tool, Borel-Cantelli lemma. Nowadays, there are lots of tools, and I mean, the biggest one comes from Martingale convergence theorem and all that. So that for very non-trivial quantities, you can say almost sure convergence quite cheaply. But Borel-Cantelli is a nice result. So now you're given sequence of sets an. They're not contained in each other anymore, general sets an. So a very reasonable notion that comes up in practice is, let's collect all these omegas which occur in infinitely many of these ANs, which belong to infinitely many of these sets. So just just mull on this notion for a while. It's easy to get confused.
How
A1 has some set of omegas, A2 has some set of omegas, yeah.
how do we define
AN is just some set on my sample space, some measurable set. All these are measurable sets. So some measurable set AN, it has some omegas. I'm looking for omegas which belong to infinitely many ANs. Not all of them, but infinitely many of them. So it's an interesting notion, right?
so
Because when I don't have convergence, then I'm violating convergence infinitely often.
so we're saying that omega occurs in infinitely many AN sets.
Yes.
So that AN has to be at least infinite, it's not a bound.
Yeah, AN is a sequence. It's A1, A2, A3 all the way. So it's a countable sequence. So this notation usually, I mean, it's a agreed terminology amongst us,
Yeah, yeah.
but this means countable.
So you're saying that if you take all omegas, which are happening infinitely often in infinitely many sets.
Yeah, collect them.
What are these sets just infinitely often? Those are these ANs.
Yes, yes, yes. I've just given you A1, A2, A3 arbitrary sets. And now you look for omegas which are belonging to infinitely many of them.
Do you
So-
want some subset? Or not even some subset. You want, yeah, it's more complex.
It's more complicated than that, yeah. It's an interesting new notion, right? Yeah. I mean, you'll see A1 has some omegas, A2 has some omegas. Now, some of these omegas belong to some of these sets. Let's collect all the omegas which belong to infinitely many of these sets.
Some omega which is then.
Not in all, infinitely many. Infinitely many, yeah, yeah. It could be that every omega belongs to a different set of infinitely many sets. That could happen. So this collection is, there's similarity, but there's also disjointedness. But nonetheless, we collect all the omegas which belong to infinitely many. And it's a very natural notion in convergence, as we said. Because if convergence is violated, it's violated infinitely many often.
So, what does the IO stand for?
Infinitely often.
And I was going to ask, why this correspond to limit soup? And I mean, I'm not saying why not just a limit?
Sure, so, but I've not come to that yet. I just want you to get the definition first. So everybody understands AN infinitely often, right? And now the point is this. So what looked like a complicated object is actually not so complicated. It's exactly this quantity right here.
What kind of AN, so this is this is our set which contains all AN and this infinitely omega.
See, omega belongs to AN infinitely often. If no matter how large my n is, looking ahead, there's still some AN which contains it.
No, my question is pronunciation. What is the set AN comma IO? Is this the set containing all AN and IO or just these omegas that we talked about?
This is AN comma infinitely often. IO just means infinitely often. It's English language.
That omegas that we talked about.
That's right. That's right. That is exactly the set we talked about.
And
Now I'm telling you that this actually has a nice representation.
this set has two objects. One is AN. The other is all the guys that are in infinitely many.
It has only, no. This means infinitely many only. That's what it means.
So this is just this is the set we talked.
This is the set.
This is basically the set of all omegas, which has infinitely many, which is in infinitely many ANs.
No confusion whatsoever on this. We can say this a few more times.
No, I'm just confused about
No, I agree with you. Yeah, that's exactly what this is. It's all the omegas which belong to infinitely many ANs.
This entire.
And that's what we are going to call AN comma infinitely often.
Okay,
ठीक है?
intuitively, so it's.
Should we repeat this a few more times, anyone?
So, does this mean that the AN and the infinitely recurring omegas, like
I think what's causing confusion is that normally when I say AN comma B, it's two sets. It's AN and B. Is that what's causing
this is
confusion?
the intersection of.
No, it's not. It's not. It's just bad language on my part. Just assume that this comma is not there. But what I mean, when you have to kind of, don't go by you just have to hear what I'm saying in this case. Often. I'm defining this set. I'm defining this notation. It doesn't go back and match with any other notation. This is all the omegas which occur in infinitely many ANs. Infinitely. Or it occurs infinitely often. Think of A as occurring in time. So that's occurring infinitely often. That's how people use it. That's why infinitely often is caught on. Yeah?
In the intersection,
Yeah.
like what's that trying to say?
Let me ask you.
So for what I for all
Let me
n,
ask you before you ask me. What does this intersection union term mean to you?
for all n, there exists n greater than m an.
For every
Yeah, but like an where the omega is like so there should be some way to import omega.
I mean, that already.
AN contains all the omegas already, right?
Yeah.
So omega will belong to this collection if for every m it belongs to some an which is for n bigger than or equal to n. So all those omegas I'm collecting.
We call an infinity often if I can take any omega, and that's infinity often.
Yeah. So it's time to kind of just sit back and think about this. So just reconcile. First was that omega, which belongs to infinitely many ANs, belongs to this set. It belongs to set AN infinitely often. Now, other way to say the same set is that no matter what your M is,
Okay, I get it.
there is some N after that which contains AN. Huh?
I thought this was like a property.
No,
this is
no.
a set itself. Like an infinity often is a completely different set.
Yeah.
Not a completely different. It's a set. Okay, got it.
Yeah. So this requires some time to get a handle on.
And this is also how we're defining Dimsu AN.
Yeah. So I'll come to that in a moment. Let's just understand this part first.
Professor, can one think of it this way? So I have the set AN.
Mhm.
Then I take a countable union of all these ANs. And then I see what are the common elements, like uncountably many M's. And I take an intersection over these. And a couple of omegas would be there in each of them. And that is why.
I mean, you're exactly saying this.
Yeah.
But a good way to understand this is something is occurring infinitely often if no matter how far I go, there's still some set which contains it.
Oh.
If something is occurring finitely often, after a while it will not occur.
Oh, yes.
So it's a very nice, clean way of thinking about this, right?
Hmm.
So no matter how large my M is, this omega belongs to this collection. If it belongs to some AN bigger than that N, N bigger than that N. So everybody with me on this?
Yeah.
So now suddenly this notation has come alive. This notation right here. It's exactly all the omegas which belong to infinitely many. Yeah. And this is called limb soup because remember how we define limb soup of sequences? It's supremum x n greater than or equal to m infimum over m. You've seen this definition of limb soup.
Yes.
Input for M.
Yeah, infimum over m.
Isn't it limit as M goes
Limbs. No, there's no inch there. There's only soup, right?
No, there's an inf there.
Lim soup is just
I need to make this thinner somehow. How do I make my pen thinner?
Ah, yes, this is it.
This is it, right?
That is how I know.
What's the other definition?
No, I mean, this is also the same definition.
It's the same definition. There's just variety of ways of kind of. So let me just write it again. Supremum of x n bigger than or equal to m. Right?
Yeah, and now we just take limb m goes to infinity.
Limb because it's a decreasing sequence, right?
Yeah.
So I can also take infimum.
Only in this case. Yeah.
In this case, yeah, we're talking about this case only, yeah.
Then we can take it.
Yeah.
Oh, so you're saying limb. Yeah.
I mean, I can also take limb. Maybe limb matches with what I'm trying to say in any case. So limb as,
Because you're calling it.
yeah, that's right. Yeah. So limb is better. So it's limb soup. But I mean, generally people write it often as infimum supremum. And that's because you've shown some properties of the supremum already. You've shown some properties of the infimum already. You've shown that supremum of random variables is measurable. Then you've shown that infimum of random variables is measurable. This way you show that infimum of supremum is also measurable. So you get that limb soup is measurable. So
Need an argument. You need.
yeah, all this. But I'm just saying that's why inf soup is kind of also a popular definition.
There's another definition which uh, you take the fact that if the sequence was bounded, you take all the convergent subsequences, take this.
Yeah.
That's it. So
Sure. So there are a lot of different representations. I mean, other nice thing is that, okay, I say limb soup is this quality. Then the point is if I go a little bit above it, then I'll stay below that infinitely, forever. And if I go a little bit below it, I'll cross it infinitely often. And that's a limb soup. That's the only one number will have this property. So just below it, I can't keep it at that value, but just below it, I'll cross it infinitely often. And just above it, I'll eventually be less than that.
Just to clarify, so there's nothing that really makes even, I mean, yeah, could equivalently call this the element for the sequence. Because there's no really concept of supreme.
I mean, yeah, so in the sense that supremum is bigger than everything, union is bigger than all the sets. Infimum is smaller than all the numbers. Here, infimum is the smallest of these sets. So it's a very clear match. It's not arbitrary, right? All right, so now that we understand this idea of infinitely often, now we have a sufficient condition for the probability of set an infinitely often to be 0. And that's when this summation is, so it's a very nice kind of compact condition that if summation of p of an is 0, then probability of an infinitely often is 0, right? So the omega is belonging to infinitely many sets. That set's probability is going to become small because each p of a of n is becoming small in this sense. Okay, how do we show this? How do we show this?
I mean, suppose not, then that guy's greater than 0.
So that would be a very natural way to think. Yeah,
But then you worry about measure 0.
it's not such an easy argument to make it to work. Yeah,
I mean, I can show that it's bounded by p and p.
I mean you're saying suppose p of an is infinity.
No, suppose, I'm saying suppose not. Suppose.
Yeah, so suppose summation p of an is equal to infinity. That's what suppose not means, right?
No, I mean, suppose q is not. Suppose not.
Suppose n infinitely often has positive probability.
Yeah. but
Okay.
Now the thing is, now the mental argument has is as an infinite sum. You show that there's some positivity to all of them.
Yeah.
But it's not easy to show because you can just say that
That's
measure
right.
0 or something.
Somehow you want to argue in your mind that suppose p of an infinitely often is positive, that means eventually all p of an are positive, and hence the summation is infinity. But it's more delicate than that, because I could construct examples where this is not true, where p of an infinitely often being positive need not mean that each of p of an is positive.
Exactly. No, so I'm not talking each of them. Just there's a subsequence that we call it. And that you can, but then the only issue you have to worry about measure being positive. Like the subset of A and I that I've chosen,
Mm.
I'll choose a subset such that there is one subsequence of A and that has positive probability. But now now the issue is that this guy might have probability 0 as well.
Yeah.
So not.
It'll be complicated to make that argument work. So in some sense, in this case, okay, it's good to just first of all see what are the tried and tested methods. What have, we kind of reconcile what's the simplest way to show this. But then you develop a tool set of how to think about and prove this thing. So in this case, it's very simple. We have this definition here already, right? So because of this countable intersection, right? Is this clear? For this countable intersection that we have, for this to be 0, by continuity, what that means is the limit of this guy should be 0. This is a probability, that limit should be 0. That will imply that the probability of intersection is 0. And why should this be, and how does this follow? Can you see this?
I mean, this
In the limit.
I mean, as you increase the n, the set becomes smaller and smaller and smaller. So eventually you'll get a set.
I want you to kind of say that this follows from this. This is what you're given.
Yeah, I mean, that set is smaller than this set.
You probably ought to use a different language.
Against what's finite.
Huh?
You can see this is.
It's finite, that's right.
You can show that
Yeah.
limit is equal to the sum.
Yeah, limit is bounded by this. Okay.
Yeah, it's bounded by the sum from n to infinity of P of n.
Uh-huh.
And that is bounded in turn by this P of overall n, because you were just not considering the first time element.
Okay, let me just ask you this. M equal to n to
Yeah, till
infinity,
infinity at of P of
P of A of n.
This is bounded.
What's happening to this as, oh, this should be M,
This is where the first zero and then.
as n goes to infinity? It goes to 0. That's the main thing. Well, that's why the sum is finite. Right? The sequence is converging to a limit because then the gap is becoming smaller and smaller. Right? This sum here, sorry. Summation P A n equal to 0 to m is converging to this guy, right? That's exactly what the summation means here. It's a countable summation. It's converging to this. It's getting arbitrarily closer to this. So the difference of the two is converging to 0. It's becoming very small. So everybody with me on this so far? All right. So now, so is less than equal to probability of this union. And that's less than equal to this quantity right here. And this is less than equal to, I can take a limit also here. What happened? Oh. Limit.
It's not getting stuck.
Oh, something happened, huh? Man, I'm ugly. Huh. What do we do? I see. Should be okay. Okay, cool. So, yeah, so this is M P of right? And that's less than equal to limit M, this summation P of A of N. Right hand side is 0, hence middle side is 0, hence this probability is 0.
That's all. The reason that the limits are simple is always because the summary, and we can't disjointify the sequence of AI that uses the argument we usually.
We don't need to. We don't need to, yeah.
So we know it's sub-additive, the probability, so you can say the union is less than equal to zero.
No, I mean, we didn't have to do all this summation on the top. Summation P of An is finite.
Right.
And that already tells you that the remainder sum,
Right, the tail sum.
yeah, tail sum goes to 0.
Right.
That's enough. You don't need anything
Highlighting
more.
the limits that you've written down by hand. The reason that.
Oh yeah, I see. Yeah, of course, yeah. The fact that the union is upper bound by the summation. Yeah, that's subadditivity. They don't have to be disjoint for that.
Right.
I mean, his point is that point that I didn't emphasize, I just kind of assume that you all know or you read up that probability of union, let's say I equal to 1, 2, let's say n, is less than or equal to summation P of I equal to 1, 2, n. This is subadditivity. This does not require disjointedness.
Yeah, it's only equal.
It's only equal if they're disjoint. Yeah. Well, I mean, it can be equal otherwise, but yeah, yeah. Then it's for sure equal. Yeah. Okay. So good. So this point is, and you can prove these things, right? So good. So now we have Borel-Cantelli lemma also with us. Let's just quickly talk about other kinds of convergence. Because with these functions, convergence can happen in variety of ways. So LP convergence, how many of you have seen this in some form somewhere? So most of you heard of LP convergence, right? Yeah. So Xn, but not in the context of random variables or even in this context? Even in this context. Yeah, but that was not probability then, right?
Not in the.
Not in the random variable setting, yeah. Okay, so basically so far we've defined this space, right? Omega is the underlying space, calligraphic F is a sigma algebra on that space, P is a probability measure assigned to that sigma algebra. Now on that space, I can come up with all kinds of random variables, measurable functions, right? I know what measurable functions are, so I can define those guys. And then, I can define their integrals. I can define integrals of absolute value of those measurable functions raised to power p. Let me collect all the random variables for which the pth integral pth expectation is finite of the absolute value. That's called the LP space, right? So LP space is just a collection of random variables with this property. All right, everybody with me so far? Okay, and now that we've got this space, we can talk about convergence in that space. If I give you a sequence of elements in that space, when is it converging to some sequence? So that turns out to be, so we say Xn converges to X in LP space if expectation of the absolute difference raised to power p is going to 0. Right?
Absolute difference of P norm.
Well, absolute difference raised to power p. Same thing, yeah.
No, but we don't take the P norm.
So P norm is just going to be, E of.
No, I get that, but we are not taking the P norm to the power P, we are taking the expectation to the power. P norm to the power P is the expectation to the power. Just see how P norm is defined, right? If you take down the power P, you get exact. Okay, take the pth fruit of that. You get the P norm. Yes, okay, I understand.
Yeah, so this goes to 0, PS rows goes to 0, same thing. Right. Okay, so this is the pth norm. And why do we call it a pth norm? Why do we call it a norm?
Have all properties.
It satisfies the properties of the norm, right? So triangular inequality is true. X plus y raised to power p, the norm.
Zero array thing. That norm is zero only if and only if X is zero.
Yeah, so that property is actually violated. That the pth norm of X is 0 if and only if X is 0 almost surely. It need not be 0 everywhere. Because expectations only depend on the positive measure set. They don't matter. What you do on a 0 measure set is your business. Right?
But yeah, the norm is defined as expectation. Okay, guys.
Yeah. I'm just saying if this norm is 0 doesn't mean that the random variable is 0.
But in expectation.
Yeah. I mean, the way around this problem is you can kind of collect all the random variables which are almost surely 0, have an equivalence class, and call them 0. And then the theory becomes clean. I mean, if you collect all random variables which are almost surely equal, that's the equivalence relationship. X is equal to y, almost surely equal to y is almost surely equal to z, x is almost surely equal to z. So one can do that extra work, but no need in this class. Okay, so we understand LP convergence, right? L2 convergence is going to be most important. So everybody with us on this? Okay. All of these random variables have to be defined on the same probability space for us to say that they have LP convergence. I say this because I can give you one random variable in one space, other random variables in some space, and still say that they are similar in some sense. In what sense will that, what can I say that? When,
Map between the two spaces.
Hmm?
Guys, about between the two spaces. The random variables, like you can represent X in one space as Y composed of that isomorphism in the other space. Does that make sense?
No, we don't need to do all that. We don't need to have the two spaces related at all. Yeah. Where I'm going with this is the idea of convergence in distribution. So we say xn converges to x in distribution. Now this idea is known to you? How many have not heard of convergence in distribution so far? You've not heard of convergence in distribution. Uh, You've not heard of it,
Word of it, I don't know.
but not really sat down, had tea, here, got to know it. Okay. All right, so let's familiarize ourselves with convergence in distribution. It comes from the idea that of central limit theorem, that if I give you sums of random variables, subtract their mean, so normalize them so the mean is 0, divide by standard deviation so that the variance is 1. That random variable in distribution, its probability distribution looks like probability distribution of normal random variables. Now, that sequence of random variables could be defined on the same space, but the normal it's converging to need not be defined at all in that space. But still, its distribution is looking like normal distribution, so it's still a valid thing to say. In some sense, convergence is happening. The probabilities associated with the random variable are converging. So you don't need to be in the same space for that, but that's called convergence distribution. So all I need is for random variable xn, I'll have a distribution function fn of x. For random variable x, I'll have a distribution function f. I don't need to have these random variables defined in the same space at all. But as long as fn of x converges to f of x, all points where f itself is continuous, need not be everywhere. Only points where f is continuous. You're allowed to not have this convergence on points where f is not continuous.
So selective pointwise convergence.
Your f is going to have at most countable discontinuities. This is your f, right? It's converging to 1.
And because that's a measure zero.
It's a measure 0 set, yeah. So you can have sequences which are kind of converging to it. Fn's are converging to it.
I thought this was a sufficient condition. This was necessary, not sufficient.
It's necessary and sufficient. Yeah, that's how we define it. Fnx converges to f of x is on the points where f is continuous. Again, be very clear. Fn, nothing to do with Fn's points of continuity. On points of continuity of f. Yeah.
How does this imply that it's a measure?
No, measure 0 set in the sense that if I give you a non-decreasing function which jumps with the points of discontinuity, each discontinuity will have a different rational from any other discontinuity. Since the total number of rationals is countable, the number of discontinuities can be at most countable. It's again one of those things you're supposed to prove, but I think Anirban will not put this up this time. All right.
Oh.
Yeah?
Why can't the discontinuity?
What's that?
Why can't the discontinuity be irrational?
No. Discontinuity means a gap. A gap always contains a rational. It contains lots of irrational, but it contains a rational number. Another gap will contain a different rational number, not the same one.
No, but the gaps on the range, not on the. Oh, yeah, so the range is 0.
Range fx is a distribution function. So when discontinuity happens, the function jumps up. In that jump, there'll be one rational number. It jumps up again, there'll be another rational number. Since the total number of rational numbers are countable, the number of jumps cannot be. It sounds like, okay, it's an overkill, few jumps while making, but you can always construct a function which has countably many jumps.
This is infinite.
Yeah, infinitely many jumps. And it's non-decreasing. So then you have to worry about these things. So these things do happen.
Didn't we just say we can't? Or is like how does this case differ from the general?
Hmm?
How does this case differ from the general case where we can cut short sequence which can have an uncountable number of this?
Well, okay, so your real question is, can I give you an example of a function which has uncountably many discontinuities? Yeah, Anirban, so let's have that as a homework problem.
And but not if it's range is 0, 1 and it's monotonic.
Still can.
You can easily have, yeah, uncountable many. Yeah.
I don't think you can. Just because of the point Prof made the rational one.
No, but that's because it was non-decreasing.
Yeah, so I said monotonic.
Yeah, but he's saying a general function.
Yeah.
Monotonic and increasing, we've established that you can't.
Just take zeros and ones.
That's right. Yeah, yes, that's what you'll do in the homework. Huh.
20 then, because this idea of less than equal to is not well defined for multiple dimensions.
Yeah,
So then what happens?
that's it. So what happens
R is
in
an R.
how do we do this in more generally? How do we define convergence and distribution more generally?
P of Borel sets match.
I mean, that could be one definition, but there's a more elegant way to define these things. So you could do that as well. Yeah.
Get mistake the discussion, but basically, so we define capital F as probability of x less than equal to small x.
Yeah.
Right. So I want to understand to say that F is continuous. I mean, probability is a map from my measure space to real numbers.
Mhm.
So what is the metric on the measure space that I'm taking? Like to be able to talk about that confidently.
I mean, does one really? I mean, every random variable x I define will induce a measure on the real line,
Right.
right? And then I can just look at this functions. So it's good to reconcile these things, but this is just equal to mu x minus infinity to x here, right?
Okay, yeah.
Now I can always define this thing for you. I mean, the reality is you'll first come up with this guy, which is discontinuous. And then you'll come up with this measure corresponding to it. And then you'll come up with underlying space where you'll assign this measure probabilities. So you can reconcile this thing, but you should not see contradictions in this. Right.
The second guy is the definition of this. So in general spaces, you have to ensure that all continuous bound functions, the limits converge.
That's right. That's right. So yeah. So now the point, his question is, how do we extend this definition? So first thing, of course, in this, the random variables did not have to be in the same space at all. They could all be in a different space. They'll all have a distribution functions. It's the distribution functions which are getting close to each other. So that's just good to be clear about.
Sure, why that?
Why do we care? Huh? Why is that the case? All I'm saying is that we have that flexibility because for the definition to work, I just need to look at distribution functions.
Define it. You cared about that measure set.
It could be different for every random variable. Random variable could be in different space. It could have its own Lebesgue measure. It could have its own induced measure.
But this convergence will still hold.
Yeah. This convergence only depends on distribution functions. So x1 is in this probability space. It has its own induced measure. It has its own distribution function. x2 has its own distribution function. x3 has its own distribution function. As long as this property is true, we have convergence in distribution. So we have that flexibility. Just to be clear that we're not tied to a same probability space. It's kind of useful sometimes, times it just confuses you. Then you have so many different concepts you want to reconcile in your mind. All right. So the point was, how do we generalize this definition beyond one dimension to, let's say, xn's which are now not just random variables in Euclidean space, but could be random elements in a general space. Each xn can be an output in a Banach space, for example, or something. We don't have to think about that right now, but Banach space. Oh, you've not been to Banach space? You guys should organize a quant-fin party there. It's does anybody want to define a Banach space?
Complete non-linear space.
Yeah, complete non-linear space. You know what a Hilbert space is? But you're doing analysis this time, right? So you'll see all this, I guess. Yeah.
Hilbert is just non-linear.
Inner norm is there, yeah.
But so not non-linear.
It's a Banach space with the inner product, yeah.
So Hilbert space is Banach space, whereas Banach space.
That's right, yeah. So L2 space will be Hilbert space, LP spaces are Banach spaces.
R and C and all of these.
All right, guys. So then for Xn, we look at a bounded continuous function f. As long as expected of every bounded continuous function converges to expectation of bounding function of x, we say Xn converges to X in distribution. Right?
They're saying these two statements are equal. Both of them.
So it's a if and only if relationship. You can argue from here, if this is true, then this would imply this in the real line. If this is true, it'll imply this in the real line. But it's a powerful notion of convergence. As I said, it's, center limit theorem kind of motivates this.
But aren't you have central limit theorem problem?
Because in center limit theorem, you have this, random variables. We'll do this, by the way. You have this sum of n random variables, Sn,
And zero.
minus the n mu upon standard deviation sigma by root n.
Goes to
This is a new random variable. Let's call it yn. And then we say distribution of yn. Probability that yn looks like probability of that's what you really say when you say center limit theorem.
Case, that's why a normal zero one might not even exist.
That's
But
right.
in terms of the distribution function, it is perfectly valid.
Yeah, distribution functions, of course, exist for random variables. So all we are saying when we say center limit theorem is that you define yn like this. So you do need random variables to be in the same space, so you can talk about the sums. And then you look at this normalized random variable, mean is now 0, variance is 1. This probability is well defined. This probability looks a lot like Gaussian probability.
So then trying to abstract this is how we got convergence distance.
Yeah.
Actually, that's what.
Right. So then you have to understand what are we saying when we say this. All right. So this is a very nice definition. Just show that sequence of random variables Xn converge in probability in distribution to X if expectation of bounded continuous functions converge basically. Now later one can show, I don't think we're going to show this, but anyone we should ask them. Convergence in distribution, convergence in probability implies convergence in distribution, but not the other way around. It's a fairly demanding thing to show, huh? Okay. But ChatGPT would be a reliable friend. All right. So now, how are we doing on time? A couple of minutes, right? We started a couple of minutes late. We really slowed down. Now that's, I mean, all of these things one can just just do a whole real analysis course on the side. So L2 convergence you can show implies convergence in probability, right? So let's understand this. E of, if expected value of xn minus x square goes to 0, this implies that probability of xn minus x greater than epsilon goes to 0. And it's quite easy to see. Anyway, you'll see it next time. But L2 convergence does not imply almost sure convergence. Just like convergence probability does not imply almost sure convergence. And almost sure convergence now does not imply L2 convergence. So almost sure convergence had implied convergence probability, but it does not imply almost sure LP convergence. And this is an example you can see right here. This example that we've been playing with so far really was an example of almost sure convergence, but expectations not converging.
But almost sure convergence, does that imply L2 convergence?
No, that's what I'm saying. Exactly, it does not. It does not.
Then I'm assuming LP convergence is a stronger notion of convergence. Then
LP is just, you have power P here. So you have to talk about, so when P is equal to 2, then it's L2 convergence.
so is that a
But I
stronger-
don't normally say LP for all P. I'll say LP for P equal to 3.2.
Oh.
But then it's not, then you're just saying different thing. But yeah, you can still ask that if I have convergence for p equal to 3.2, do I have convergence for p equal to 2? And the answer is yes.
So my question is like, which one of them is like stronger that convergence, or are we even allowed?
No,
to
like I
have
told you,
convergence?
stronger is when p is larger.
Oh,
Larger the p, it implies
let's take L2 convergence.
yeah.
And almost sure.
So L2 convergence, for example, will imply L1 convergence.
Hmm.
But both of these will not imply almost sure convergence.
Okay.
And almost sure convergence will not imply either of these.
This does not converge almost vertically.
It does converge almost surely to 0. It does, right?
No, because if you take n to infinity, infinitely many omegas will be in.
No.
Oh, sorry, omega is now 1 to 1 by.
No, so only for-
Yeah, yeah.
Yeah, but this is
Yeah,
a
yeah.
different example.
We are doing a
So
different
this is-
example now. Yeah.
This is, just to be clear, if you have convergence in any LP, you will have convergence in all LQ as well, right?
When Q is less than P.
Q is less than.
Yeah.
Acha, okay, Q gives himself power here.
There's a monotonicity about this LP norm. LP norm is monotone, right? So the second norm is less than the third norm. So if third norm is going to 0, second norm is also going to 0.
Because also continue, okay. And
Right? Okay, so we'll do all of this, I guess. Next time we'll start from this slide. We won't do a review much, but
What about L2
and then we'll do law of large number. I'll just tell you very quickly. And then I also actually prove strong law of large numbers. This is just to kind of getting your hands dirty in probability. In this course, I can do that because I think you guys will benefit from seeing all this.
What would the big picture be from here?
Well, so I just want you to get very familiar with probability notions. We want to then do conditional expectations in a very nice way. So you understand conditional expectations really well. Those are crucial for explaining martingales. So martingales is something that you have to understand really well. Then we'll go to Brownian motion and Brownian motion along with martingales. And those are building blocks for stochastic calculus. And stochastic calculus is building block for finance. So maybe in 2028, we'll reach finance. Okay. All right. Bye, everybody. I see that there are no questions here in the audience. All right. So this is, it's a academic class of undergraduates. So I'm focusing more on theory than I would have to an audience which wanted to learn just finance. But it's probably worthwhile. Thank you, everyone. I'll see you next Tuesday. So good. This is.